right. Just a second here. Right, we'll take a look at a new chapter today. This is on amino acids. And in just a minute, I'll share my screen. Okay. Right. Just a minute here. All right. Okay, I'm going to share my screen. Okay, as soon as this loads, we'll get started. Okay, we've looked at amines, and then we've also looked at carboxylic acids. And now we'll look at compounds that contain both of these groups, namely amino acids. Let's get this over. Okay, amino acids are compounds that contain both an amino group and a carboxyl group. Most amino acids are what we call alpha amino acids, and these are ones in which the amino group is on the carbon adjacent to the carboxyl group, in other words, carbon number 2. Although alpha amino acids are commonly written as the unionized form, they are more properly written as the zwitterion. A zwitterion is an internal salt. Okay, so in structure A, okay, although amino acids are often written this way, okay, especially at physiological pH, they're going to exist as this zwitterion or dipolar ion or internal salt. The amino group is basic and the carboxylic acid group is acidic, so there's a proton transfer that takes place. With the exception of glycine, all protein-derived amino acids have at least one stereocenter, and that's on the alpha carbon, and are chiral. The vast majority will have the L configuration at their alpha carbon. Okay, so what do we mean by the L configuration? Okay, if we write the amino acid in the Fisher projection like this, carboxylic acid at the top, we draw this carbon skeleton from top to bottom. Okay, in 3 dimensions, this is the chiral center right here. Vertical groups are back, horizontal groups are forward. Okay, so this is the L configuration. It has the amino group on the left. And this is the configuration for most naturally occurring amino acids. Right, so you have the carboxyl group. Right, you have the carboxyl group, you have the amino group, and for most of the common amino acids except one, which we'll mention, this will be a primary amine. And okay, where we have glycine, R would be H, and we would have 2 groups the same, and so that's the only one that doesn't have the chiral center. Okay, so here are some nonpolar side chains. Okay, so where alanine, for alanine, the side chain is a methyl. Okay, so we got the carboxyl, amino, hydrogen, and methyl, 4 different groups. Here's glycine, we've got 2 H's, so that's not chiral. Isoleucine, where we have a sec-butyl group. Leucine, where we have an isobutyl group. Methionine, we have a sulfide or thioether group. Phenylalanine, where we have a benzyl group, a CH2 and a benzene ring. All right, this is the only common one in which we have a secondary amine, and this is called proline. Okay, this is tryptophan. This is called an indole group. We have a CH2 and an indole group, and then valine with an isopropyl group. Okay, so these are nonpolar side chains. There are 20 common amino acids that are found in proteins, and these are just a few of those. And at pH 7, okay, both these groups are ionized. Okay, then we have some with polar side chains. Okay, okay, notice that these have both a 3-letter and a 1-letter abbreviation. Okay, so asparagine is ASN or just N. The 1-letter abbreviations are becoming more common. Okay, so this has an amide group as the side chain. The amide nitrogen is not basic, but this group is polar. Glutamine, okay, again, an amide group. Serine, where we have an alcohol. Okay, this is not basic, but it is polar. And then threonine, another alcohol group. Okay, some of the amino acids have acidic or basic side chains. Okay, on the left, we have the ones with the acidic side chains. And these include aspartic acid, Okay, and at pH 7, this is predominantly ionized. Glutamic acid, cysteine. Okay, remember that the thiol group is more acidic than the alcohol group. Okay, not as acidic as a carboxylic acid. So it is acidic, but notice at pH 7 it's not ionized. Okay, and then tyrosine has a phenol group. Okay, if we were to raise the pH a little bit, then the thiol and the phenol would both be ionized. Okay, this is for pH 7. Okay, and then we have 3 amino acids that have basic side chains. Okay, this is arginine. This is called a guanidine group on the arginine. This is fairly strongly basic, at least compared to most amines. Okay, when we protonate this nitrogen, okay, that plus charge gets spread out by resonance among all 3 of the nitrogen atoms. Okay, this is histidine. We have an aromatic heterocycle here. Okay, this nitrogen is not basic, but this one is, the one without the H. And then lysine has an amino group. Okay, these are some other common L-amino acids. We have ornithine, citrulline. Okay, it has this is the carboxamide derivative of ornithine, where we form an amide here. And then this is 4-amino-butanoic acid, also known as GABA, gamma-aminobutyric acid. This is a neurotransmitter. Okay, so here are some pKa values for ionizable groups of amino acids. Okay, notice that the carboxylic acid group has a pKa of around 2. Okay, that is, amino acids are more acidic than regular carboxylic acids, which are about 4 or 5, so about 100 times more acidic. The amino groups, turns out, are actually less basic than isolated amines, a little bit less basic. Okay, so these are the pKa values for the amino groups. Okay, notice they're on average about 9 for the pKa of the conjugate acid. Okay, and then the ones that have acidic or basic side chains, the ones with basic side chains, okay, like arginine, which has a basic side chain 12.48. Here's another one, lysine and tyrosine. And then we have some that have acidic side chains, like aspartic acid. Okay, so it has a low pKa for its side chain, and glutamic acid. Okay, and then this last column is something called the isoelectric point, or PI. Okay, what this is the pH at which, let's back up here, at which the zwitterion is the dominant species. Okay, if we lower the pH, if we make it more acidic, okay, nothing will happen to this, but this will accept a proton. Okay, if we make it more basic, then nitrogen will lose a proton. Okay, so the isoelectric pH is where the is where charges are balanced, where the zwitterion is the dominant species. Okay, this is some more of the same information. Okay, the average pKa of an alpha carboxyl group is 2.19, which makes them considerably stronger acids than aliphatic carboxylic acids, such as acetic acid. The greater acidity is accounted for by the inductive electron withdrawing effect of the NH3 plus group. Okay, since nitrogen has a plus charge, it's going to pull electrons, and that will help stabilize this anion. Okay, without that amino group, we don't have that inductive stabilization. Okay, so this is a difference of roughly 2 pKa units, so that means this is about 100 times stronger. Okay, the effect, however, decreases with distance. Okay, so if we have a an alpha NH3 plus, like as for alanine, okay, then pKa is 2.35. Okay, if we have a carboxylic acid group that's beta, okay, then it drops off about tenfold, and then for glutamic acid, where we have a carboxylic acid group on the gamma position, then the pKa of that side chain carboxylic acid drops off even further. Okay, and it's becoming pretty close to that of an ordinary carboxylic acid. Okay, the average pKa for an alpha NH3 plus group is 9.47 compared to the average value of 10.76 for primary alkyl ammonium ions. Okay, so that's about a tenfold difference. Okay, here we're talking about the acidity of the NH3 plus group. Right, the side chain of arginine contains a guanidine group. And this is what I was talking about earlier. Okay, this is resonance stabilized when we protonate it, and then the plus charge is spread among all three groups. Right, the imidazole group is a heterocyclic aromatic amine. Okay, for review, an aromatic compound has to be cyclic. It has to have a p orbital on every atom of the ring, unhybridized p orbital, and it has to have a Huckel number. In this case, it is 6. So 2, 6, 10, 14, and so on. Okay, so this has the requirements for an aromatic ring. The lone pair on this nitrogen without the H, okay, that is in the plane of the ring. Okay, that's not in a p orbital. For the lone pair on the NH, okay, this one is actually part of the pi system. Okay, and so if we protonate this one, that totally disrupts the aromatic character. And so this nitrogen is not basic. Okay, this nitrogen is. So when we protonate that, it's still aromatic. All right, this is a titration curve for glycine with sodium hydroxide. Glycine is a weak acid, and halfway to the first equivalence point, the pH will equal to pKa 1. Okay, this is a buffer region in here. And then, since this is a diprotic acid, okay, at the first equivalence point, the pH will equal the isoelectric point. And this Vitter ion will be the dominant species. Okay, and then we'll have a second equivalence point, or a second equivalence point up here, second buffer region. All right, the isoelectric point, or PI, is the pH at which the majority of the amino acid molecules have no net charge. The PI for glycine, for example, 6.06, falls between the pKa values for the carboxyl and amino groups. Okay, so if we average pKa1 and pKa2, we get the isoelectric pH. Okay, and here are those values. This is pKa1, pKa2. That's for loss of a proton from the NH3 plus group. Okay, here's another table of the isoelectric pHs. These are for polar and non-polar side chains. Okay, notice that most of them are around 6. For acidic side chains, okay, they are lower. The isoelectric point is lower. If the side chain has a carboxylic acid, okay, then the PI is about 3. For cysteine and tyrosine, cysteine has a thiol group and tyrosine has a phenol group. If we have basic side chains, okay, notice the PI is higher than 6. Okay, in the laboratory, electrophoresis is the process of separating compounds based on their electric charge, okay? Many of you might have done electrophoresis in the lab. Okay, we can do electrophoresis of amino acids using various media: paper, starch, agar, certain plastics, cellulose acetate, for example, as solid supports. For paper electrophoresis, a paper strip is saturated with an aqueous buffer of predetermined pH, and that serves as a bridge between the two electrode vessels. Okay, so here's a simple diagram of an electrophoresis apparatus. Okay, so we have a buffer solution, we have the paper or other solid phase. Okay, we have the sample. Okay, and then we apply an electric potential. The amino acids will migrate toward the electrode with a charge opposite of their own. Okay, molecules with a high charge density will move faster than those with a lower charge density. And molecules that have an isoelectric point where the charges are balanced will remain at the origin. Okay, so after the separation is complete, the strip is dried, developed to make the separated amino acids visible. Okay, one way of visualizing that is to use this reagent called nenhydrin. And when I was at K-State, we always liked nenhydrin because it was purple. Okay, it forms a purple colored anion. Oh yeah, I got some nenhydrin. Yeah. Yep. Okay, this is the purple colored anion that's formed. Okay, next we're going to look at polypeptides and proteins. In 1902, Emil Fischer proposed that proteins are long chains of amino acids joined by peptide bonds. So what is a peptide bond? It's a special name given to the amide bond between the alpha carboxyl group of one amino acid and the alpha amino group of another. Okay, so carboxylic acid and an amine split out water to form an amide, which is a peptide bond. Right, a peptide is a short polymer of amino acids joined by peptide bonds. They're classified by the number of amino acids in the chain. Okay, for 2 it's di, for 3 it's tri, and for many it is a polypeptide. And for an even larger chain, that's a protein. Protein is a biological macromolecule, typically of molecular weight 5,000 grams per mole or greater, okay, consisting of one or more polypeptide chains. Okay, so here is serial alanine. Okay, we form a bond between the carboxyl group of serine and the amino group of alanine. Okay, split out water, and we get this dipeptide. Okay, the order in which these appear. Okay, we start from this side. This is called the N terminus, and this is the C terminus, where there's a carboxylic acid. Okay, this is different from the dipeptide in which these would be reversed. Okay, that's different from allosyr, or AS versus SA. They're two different dipeptides. Okay, by convention, peptides are written from left to right, beginning with the free NH3+ group, which is called the N terminus, and ending with the free carboxylate group, which is also called the C terminus. Okay, so here's a tripeptide of serine, phenylalanine, and aspartic acid, sorry. Okay, this sequence of amino acids in a polypeptide chain, okay, read from the N-terminal amino acid to the C-terminal amino acid is called the primary structure. Okay, so the primary structure is the number, kind, and sequence of amino acids in the chain. Okay, we can determine amino acid in that sequence by hydrolysis of the polypeptide. This can be carried out in, for example, 6 molar HCl at elevated temperature. Actually, I'm sorry, this will tell you which amino acids are present, not necessarily the sequence. Okay, so the quantitative analysis of the hydrolysate takes place by ion exchange chromatography. Okay, so this will tell you what amino acids are present. Okay, because we use HCl just to hydrolyze everything. Cyanogen bromide, or BRCN, is used to cleave peptide bonds specifically formed by the carboxyl group of methionine. Okay, whereas the 6 molar HCl was non-selective. Okay, and then we can also do some selective cleavage using enzymes. Okay, for example, trypsin and chymotrypsin. Okay, these will catalyze hydrolysis of a peptide bond formed by the carboxyl group of, okay, in the case of trypsin, it would be arginine or lysine. For chymotrypsin, it would be one of these 3 amino acids, phenylalanine, tryptophan, or tyrosine. Okay, so what this does, this and cyanogen bromide, this will give us smaller fragments to work with. Okay, and then we can remove amino acids using something called the Edman degradation. Okay, so this cleaves the N-terminal amino acid of a polypeptide chain. Okay, and so these are various examples of deducing primary structure of a pentapeptide, for example, from experimental information. Okay, nowadays they have automated peptide sequencers. Right, the 4 atoms of a peptide bond and the 2 alpha carbons bonded to it lie in the same plane with bond angles of 120 degrees about the carbon and nitrogen. Okay, and that's what this is showing here. Okay, these 2 alpha carbons and the CO and the N are in the same plane. Okay, Linus Pauling proposed that a peptide bond is most accurately represented as a hybrid of 2 contributing structures, which are shown here. The rotation about this CN bond is highly restricted because of the double bond character. And so it tends to maintain its planarity. Virtually all peptide bonds and naturally occurring proteins studied to date have the trans configuration, okay, which is right here. Okay, so there is restricted interconversion because there's a lot of double bond character between the C and the N. Okay, many proteins will also have secondary structure, and this consists of the ordered arrangements or conformations of amino acids in localized regions of a polypeptide or protein. To determine from model building which conformations would be of greatest stability, Pauling and Corey assumed that all 6 atoms of each peptide bond lie in the same plane and have the trans configuration, and that there is a hydrogen bonding that occurs between the NH group of one peptide bond and the CO double bond group of another peptide bond, as shown in the next screen. Okay, so we have hydrogen bonding here between the NH and the oxygen of another amino acid residue. Okay, and on the basis of model building, Pauling and Corey proposed that 2 types of secondary structure should be particularly stable. Okay, these are the alpha helix and the anti-parallel beta pleated sheet. alpha helix is a type of secondary structure in which a section of a polypeptide chain coils into a spiral. And most commonly, it's a right-handed spiral. Okay, so it looks like a coiled spring. And hydrogen bonding occurs between the oxygen on a carboxyl group and the nitrogen 4 amino acids ahead of it, the alpha helix. Okay, and it turns out that in order to have the alpha helix, all of the amino acids have to be L. If you have a mixture of D and L amino acids, you can't make a alpha helix. Okay, so this is looking down the axis of a helix for polyalanine, where we have a string of alanines. Okay, some of the features of the alpha helix. There are 3.6 amino acids per turn. Each peptide bond is trans and planar. NH groups of all the peptide bonds point in the same direction, which is roughly parallel to the axis of the helix. CO groups of all peptide bonds point in the opposite direction, also roughly parallel to the axis of the helix. The CO double bond group of each peptide bond is hydrogen bonded to the NH group of the peptide 4 amino acid units away from it. Okay, and then all R groups, or side chains, point outward from the helix. Okay, the other type of secondary structure is the anti-parallel beta-pleated sheet. Okay, this consists of adjacent polypeptide chains running in opposite directions. Each peptide bond is planar and has the trans configuration. The CO and NH bonds of peptide bonds from adjacent chains point toward each other and are in the same plane. Okay, all R groups on one chain alternate, first above, then below the plane of the sheet. Okay, so in the alpha helix, you have intramolecular hydrogen bonding to make the coiled spring. Here we have hydrogen bonding between chains. Okay, and this gives it kind of an accordion shape, pleated shape. Right, tertiary structure is the three-dimensional arrangement in space of all atoms in a single polypeptide chain. One of the ways in which tertiary structure is maintained is by disulfide bonds between cysteine residues. This disulfide bond formation and reduction is reversible. Okay, here's human insulin. There are two chains, one consisting of 21 amino acids, another consisting of 30 amino acids. These are connected. We have some connections with disulfide bonds, and we have another disulfide bond here. All right, myoglobin consists of a single polypeptide chain of 153 amino acids plus a single heme unit. The heme unit is shown right here. This is heme. That's found in both myoglobin and hemoglobin. Quaternary structure is where you have several folded chains which are not connected to each other, and quaternary structure describes how they're packed in a three-dimensional space. Okay, so the major factor stabilizing the aggregation of polypeptide subunits is the hydrophobic effect. The hydrophobic effect is the tendency of nonpolar groups to cluster together in such a way as to be shielded from contact with an aqueous environment. Okay, so here's hemoglobin. Hemoglobin consists of 4 chains, 2 alpha, 2 beta chains, that are packed in a specific 3-dimensional arrangement. Okay, here are just some examples of proteins that have quaternary structure. All right, so going back to secondary structure, hair, keratin in hair has primary structure, and then it has alpha helices, but the helices are not folded, so it does not have tertiary structure, just primary and secondary. Silk is another example. It does not have tertiary structure, so the chains are not folded. Silk consists of straight chains in a beta pleated arrangement. Okay, the slideshow only showed disulfide bonds as maintaining the folding or 3-dimensional structure. There are several other ways in which 3-dimensional structure can be maintained, including hydrogen bonding and what are called salt bridges, salt linkages. Okay, so we can have an ion such as magnesium. Okay, this is called a salt bridge. We have either one chain or one part of the chain. And we have a divalent ion such as magnesium or some other ion in here. All right, and then when heavy metal poisoning occurs, heavy metals such as mercury and lead often will replace the metals occurring in salt bridges with new salt bridges. Polar solvents such as alcohol, such as the isopropyl alcohol wipes, these help to denature proteins by disrupting hydrogen bonds and forming new hydrogen bonds. All right, so that concludes our chapter on amino acids and proteins. All right, no class on Wednesday, it's a holiday, so I will see you virtually on Friday.